I hope this topic connects well with some of the other things at this workshop. Please, of course, interrupt with any questions since it's a mini course. Okay, so let's say that G is a semi-simple Lie algebra. One thing, and let's say V is a irreducible representation. One thing of interest is the endomorphisms of V tensor N as a representation over. So endomorphisms is V tensor over G. So this is a centralizer algebra. So I'll just remind you some examples of this, which I think we saw yesterday in the talk, so I wasn't there. If G is equal to SL2, then this algebra is called the Temperley-Lieb algebra. More precisely, like the Temperley-Lieb algebra specialized at Q equals 2. Sorry, V is SLN, sorry, G is SLN and V is C2. Then this is the Temperley-Lieb algebra. So in terms of generators, you can write it like so. Generators EI with relations EI plus 1, EI equals EI, and EI squared equals 2 EI, and EI EJ commute if I and J are separated. And in terms of diagrams, you can picture it as follows. So this is an algebra of diagrams. So they leave diagrams. So they look as follows. You take endpoints up here and endpoints down here, and you consider a cross matching, for example, like so. Temperley-Lieb algebra is the span of such diagrams where the multiplication operation is given by stacking, and you use the rule that a circle becomes 2. So under this diagrammatic description, EI corresponds to the diagram, which looks as follows, taking I and I plus 1. And how does this isomorphism here work? Maybe everyone's familiar with it, but just to make sure everyone's on the same page, this EI guy, it corresponds to a map from C2 tensors itself n times. You call these C2s. You take just the I and I plus 1 copies here. Those two copies use the contraction map, which maps them to C, to eliminate those two factors. And then you include the copy of the trivial representation back into C2 tensor C2. That's why it's drawn as this diagram, because I didn't say that. Yeah, oh no, I did say that. So it looks like this diagram because you go from these two copies of C2 to the trivial representation and then back to C2. And the other strands representing the other tensor factors are unchanged. So we're going to be interested in this kind of diagrammatic description of these centralizer algebras, or more generally, the thing I'm about to say. But first, let me just do one more example. If G is equal to SLM, then there's a map by the Howe Duality CM standard representation. There's a surjective map from the group algebra of Sn, and this map is an isomorphism if M is greater than equal to N. I'm going to adopt somehow an approach, a little bit different approach in this mini course. We're going to consider the following thing. So we're going to choose some set S, a set of irreducible representations. And maybe just for simplicity, it's going to be closed under duals. So if V is an S, then V dual is also an S. Although the truth is that this business about duals is creates a lot of headache in this topic. So I'm mostly going to sweep these duals under the rug in my talks. I'm going to consider what I'll call rep SG. So this is the monoidal category whose objects are tensor products of representations in S. Consider arbitrary tensor products where each of these VIs lie in S. And it's a monoidal category where you can tensor more strings like this. That I'm going to discuss generators and relations for rep SG as a monoidal category. Explain what I mean by that. Well, if we look at this this algebra here, this Temperley-Lieb algebra, already there's something a little bit redundant about the description. Look, I wrote one algebra for each n with many relations. But when I drew it as pictures, I could say, oh, it's just these pictures with just this one relation. And in fact, they can be made precise in this categorical language. So if we work here with SL2, so now this example, but revisited in this categorical language. So if we think just wrap, and my S is just going to be the standard representation, so like the set containing just C2. This has just one generator, the representation category. Like the morphisms in the representation category has one generator, or maybe two generators. Those cups and caps, and the relations. Maybe like there's this relation which is basically just expressing that the cup and the cap are the units and co-units of this duality, and this circle relation. For example, this guy here, diagram which would look like so, which would correspond to the map from C2 tensor n to C2 tensor n minus 1 and minus 2. Right? This is expressed in terms of these generators by using this monoidal structure. So this is the map, which is this morphism is given by like the one tensor this cup morphism tensor 1. Using the structure of a monoidal category, you can start with just very simple generators and construct morphisms for larger tensor products. So the flexibility about working with the generators and relations monoidal category rather than each algebra individually is you can much more concisely present the this like empty diagram means, I mean, if I picture this so in this algebra language, this relation would be like, if I have a circle somewhere in the midst of my diagram, I get 2 times the rest of my diagram. And in this categorical language, this circle is being viewed as a map from C2 tensor C2, sorry, from C to C2 tensor C2, and then back to C. So I'm analyzing this thing like so. So here, when I have no diagram, it means just maybe I should spell this out a little bit more precisely. But the objects of this, like, let me be slightly more precise, because otherwise I think it could be confusing. Let me spell this out a little more precisely. So in other words, I define a category, objects of my category, sequences of dots along a line, some number of dots, possibly none, along a line. And the morphisms are, well, kind of like these template diagrams, but now it could be different numbers of dots. So linear combinations of these diagrams. And maybe you could say the diagram's allowed to have a circle in it, but modulo the relation that anytime you have a circle, it becomes twice the identity. So this is like, it's a little confusing. Maybe the colored chalk would have been helpful. So this is a circle, not the number 0, and this is a scalar 2 times the identity.
In the case of your example, rep C2 SL2 is the full category of finite dimensional representation, right?
No, it's not quite the full category, because the objects, I'm only considering tensor products of copies of C2. I mean, every other representation can be realized inside there, but I'm not those objects.
Finite sum.
This category is not a. You could then take the Kubi envelope to get the full representation category of C2. But the definition of this category is the objects are just tensor products of these fundamental representations. In this case.
The point is that you have an empty product. So you have to have a version of it.
Yeah, and well, among the, maybe I should say, among the lists, you could have no, like this n here is
N could be 0.
Yeah, n could be 0. So like the empty tensor product is allowed, which corresponds to the trivial representation. Yes. Yeah, so there's a diagrammatic category defined like so, and the statement, like when I write this thing, I'm saying that this diagrammatic category is equivalent to this category of representations of SL2 where the objects are tensor products of C2s. Of course, this n dots becomes the n full tensor product of C2s. And if I was being a little bit more precise, I wouldn't speak just about monoidal categories, I would speak about monoidal categories with duals, what's called a pivotal category. And then these cup and caps are like already built into the pivotal category structure. So I would have no generators in one relation. But this dual stuff is like a little bit annoying, so I prefer to sweep it under the rug, so I won't talk much about dual. Having already said that twice now, you're very suspicious, I know. Okay, so this, I guess, theorem that there's a diagrammatic description of these temporal algebra or of this category. At least I've seen people attribute it to some like 1932 paper in German where Hermann Weyl was one of the authors. Anyway, it's some kind of classical result. But I would say the modern like origins of this kind of diagrammatic descriptions comes from a paper by Greg Cooperberg. So this is maybe example number 2. So Greg Cooperberg in 97, he proposed like sort of systematically studying these diagrammatic categories. And he considered G to be SL3, and not just the standard representation, but also the other fundamental representation too. So the standard representation is dual or wedge 2C3. So that was his set S. And then there's some obvious generators. So then I'm gonna label like instead of just dots on a line, I'll have to tell you which representation they are. So this guy will be labeled with a 1 and this one with a 2. So an object in this category might look like a sequence of 1s and 2s along a line. That corresponds to some tensor product of C3s and wedge 2C3. And the generating morphisms will be as follows. So there's some obvious, of course, morphisms. You take C3, tensor C3 to wedge 2C3. So we need a diagram for that. So we'll just make this trivalent vertex. So it's a 1 and a 1 come in and a 2 comes out. So that's now a diagram. And then, then I also have C3 tensor wedge 2C3 goes to the trivial representation because wedge 2C3 is the dual of C3. And I draw that, so I draw that like this cup. And then these and their flips are all the generators. That a circle labeled 1 has the value 3 to be the map from C to C2 tensor C3 tensor wedge 2C3. So it's like labeled 1 on this side and labeled 2 on this side. But usually I'll suppress the other side. It's obvious. You can also get rid of these labels of 2s by making arrows. So actually, I think the way Cooperberg did it is he wrote this thing like so. You can write this, you can write an arrow up when you have a 2. But for what I'm thinking later, it's more convenient to have these numbers too. So I'll use them. Anyway, so this circle, whoops, so you start the trivial representation, you create C3 tensor wedge 2C3, and you go back using to the trivial representation. And of course, there's not like a unique morphism from C to here. There's a scalar here, and there's a choice of a scalar here. But it's sort of a natural, well, there's maybe not that natural way to fix it, but you can choose these scalars so it comes out to 3. And that somehow makes things work out better later. You have this relation, and I feel like I must be leaving out a relation. Okay. Another relation that you have is if you have a wedge 2C3, you can convert it to 2 copies of C3, just the usual inclusion of wedge 2C3 into C3 tensor C3, and then map back to wedge 2C3. And this is like V wedge W goes to V tensor W minus W tensor V. And then if you're normalizing it, so this thing goes back to V and this one goes back to V wedge W and this one goes back to W wedge V, which of course is of negative W wedge V is V wedge W. So this overall becomes twice W wedge V. So you get scalar of 2 pop out. Okay, so again, this is the scalar, this is the label on the representation.
I have a question from the Zoom. When you flip the cup, do you label the legs 1 and 2 or 2 and 1, or it doesn't matter?
Well, yeah, sorry, maybe I should keep. You have 4 of these guys.
Oh, okay.
Yeah, doesn't matter. Again, you could try to be more careful. I feel like I missed one of Cooperberg's relations, but it doesn't matter too much. Maybe I can come up with it off the top of my head. I can write this down. But there should be a relation that looks like so. So you can have 1 and 1. The relation which involves a kind of breaking up a square. But now that I should have read it down ahead of time, but I forgot about that. Anyway, so there is another relation that I've not written down, but not a long list of relations. And Cooperberg did this not just for SL3, but he did it also for the other 2 rank 2 Lie algebras. he also wrote diagrammatic lists. And he proposed the problem of trying to do this for every semi-simple Lie algebra. So the next in the development of this subject, I would say, there was a student of Kuperberg named Kim who worked on the SL4. And then there was a thesis of Scott Morrison who had a conjectural description for SLN. And then then there was our paper. So this is from 2012, I guess. That's my Sabin Cottis, myself, and Scott Morrison. We studied SLN. Maybe I'll call it SLM to just distinguish it from the n-fold tensor product. SLM, and the set of representations that we'll take will just be the fundamental representations. So Cn, wedge Cm, wedge 2Cm, and so on. And generators are maybe what you might expect based on what you've seen in this SL3 example. So you can put together a wedge K and wedge L and get wedge K plus L. You can pair wedge K and wedge L. And that's it. And you can flip them. So this is way down. So that's wedge K Cm tensor wedge L Cm wedge K plus L Cm. Again, there's some choice of normalization, exactly what you choose, but the natural thing would just be kind of to wedge the two guys. And there's the relations, and they go like so. Well, just a circle labeled K has the value of n choose K.
You don't include the scalar.
So everything is like C linear categories. So there's automatic. Oh, you mean not the top exterior power? Well, it's SLM, so that would be the trivial representation.
Yeah, so you include that.
It's sort of like automatically included in the sense that the objects of this category are these, again, tensor products of these things. So tensoring with the trivial representation, it's like having one less, you don't have that representation. Like as someone commented earlier, if you take the empty tensor product, that's the trivial representation, or the unit object in the spinoidal category. So the relations are a circle labeled K has the value n choose K. So again, the circle labeled K, it's you take the trivial representation, you create wedge K Cm tensor and wedge L Cm, and then you return to the. Anyway, then you have some other relations that are not very interesting. I'm just going to write some of them down just for completeness. So if you take a K plus L strand, split it into K and L, and then recombine, you get another binomial coefficient. Then maybe you get something, which is the one I was sort of trying to write down off the top of my head there and then decide not to. So if you have two guys coming along, K and L, you can this way, you can split off. In fact, you can split off amount out this way, but let's just split off one guy out this way to join this side. So you have like a K wedge here, an L wedge here. You split one guy off from the L wedge, he goes and joins the K wedge, and then you split one guy back. But it gets added, so it's not just like the identity. So it gets like permuted around in this wedge here, it comes back, and now you're back to where you started. Or you could do it in the opposite direction, and that is equal to K minus L times the identity on these two things. And so the identity is just drawn as the identity map from wedge K tensor wedge L to itself, just drawn like so. So the difference between sending one guy here and sending one guy back and this way is K minus L times the identity. So this might already remind some people of something which is coming up soon. And then there's a few other ones too. Let me not bother, but a small list. The history is actually interesting in that before our theorem, so Scott Morrison, my friend, in his PhD thesis from a few years before this, he had a conjectural list of the relations, but there are much more relations than we have in our final list. So we proved with conjecture, but I mean, his list of relations was far excessive. In fact, he had polygons of arbitrary size appearing in his relations. So here we have like some small things. They're like more and more relations with more and more strands, but it can all be reduced to just extremely few. And even in SL4, this other guy, Kim, he had more complicated relations than than are necessary.
So your prop is not called FK.
Sorry?
Your generator of the prop. Is that for arbitrary thing?
Oh, sorry. Of course, I need to be doing. So the method that we use, this is what I'm going to explain soon, is this method called, well, this Howe duality. So that's how we did this. So after our work, so I would say between here and here, there wasn't too much progress, but since our work, this has become a popular subject, and there's been a whole lot of papers. So I just quickly write down some more recent progress in this topic, just to show you that it's that it is very active. And this, what I'm writing down is not even a complete list of all the papers in this topic, but just a few notable work. So pretty soon after our work in 2015, Tubenhauer, Vaz, and Wendrick, basically they extended our work. So instead of just taking the wedge representation, they took the sim representations too. So they took the set of tensor products of exterior powers along with symmetric powers. And of course, there's a lot more symmetric powers than exterior powers. And what's interesting is it's not so easy to do just symmetric powers on their own. But when you allow yourself to have both symmetric and exterior powers, somehow you can make this kind of web description. And then a little later, or like this is a representative paper by Brown and Fujawa. They took G, so this was again still in G as SLM, but now these people started doing it for other G's. And they took a sort of, well, not even G. They studied type Q Lie superalgebra, which is not some subject I know much about, and the fundamental representation. And then, I mean, there was also other works about different other class of Lie superalgebras and other works, but maybe the most recent work just from last year, back in the realm of classical Lie algebras, take G to be SP2N. And they gave a complete description, pretty analogous, like a set of relations which looks, short list like ours, but now for the symplectic Lie algebras. And this was Bodish, Elias. I guess here S was the fundamentals.
Q stands for pairs.
Why is this called type Q? I never completely understood, but like in the normal, I'm not an expert on super algebras, but in the normal Lie algebras is like A, B, C, D, and so on. And then for super Lie algebras, yeah, and I think it stands for queer, yeah. But why was there a reason? There's also a type P.
Paraplegic.
Yeah, but why did they jump to P and Q just for fun? Was there a different reason?
Yeah.
They just wanted to be queer, or maybe they really want to use a paraplectic, peculiar and queer. I see. I mean, I don't know. Yeah, I'm not sure why these guys particularly were interested in this.
So if you take generators, if you take tensor product, you look at this decomposition in symbols again, which is actually very important for construction. It's just always not just.
Well, if you took two of them and decompose them, if you have an arbitrary list and decompose them, it won't be multiplicity free. But actually, the truth is that this method of web descriptions doesn't really use this decompositions into simples. In fact, this theorem, while I stated it over C, it actually holds over fields of prime characteristic 2. I mean, not 2, but fields of prime characteristic as well. I think maybe any characteristic, or at least sufficiently large characteristics, but where we don't have any semi-simplicity, so we don't even have a decomposition. It doesn't really involve that. Yeah, and actually we worked over C, but I think Ben Elias proved that it works over, that this method works over, that this theorem holds over any character. So actually, the funny thing is this decomposition into irreducible is not very important.
This is also our quick one.
This kind of web description, or?
Yes.
From what year? Okay. So for SLM and prime characteristic. So Ben Elias has a paper about this. Well, among other things, he does this. I don't know what year it is, but yeah, it's approximately. And then
Around
it's not very alphabetical. That's her name, right?
describe simplification of the technical thinking.
Oh.
For P is less than.
Oh. Oh.
For that we need this.
Okay, so yeah, so this category, so yeah, well, that was a good segue into my next topic, which I was going to say, why would you be interested in finding such categorical presentations? So one reason that I was kind of arguing in the beginning was it gives sort of like a very, I don't know, compact description of the category. You just need to say a very small amount of things, but there's actually, as Pavel said, you can actually use it to prove things that you might not be able to prove otherwise. So for example, in prime characteristic to study these representation categories. So for example, Ben Elias was interested in it because he used it to connect with Sorgo bimodules. But now I should explain maybe why Greg Kuperberg was interested in the first place. There's of course a map for any two representations from V tensor W to W tensor V. And this map can be drawn by such a diagram like this. I label this V and this W. And once we have this, you might say, where does this kind of map appear in my categorical description? Because it wasn't there. But once we have this categorical description, diagrammatic description, you can write this map in terms of those diagrams. So for example, if you just take, say, CM, tensor CM, just the, well, this might be the identity map, but it's not the identity map. And this map, this permutation of factors map, you can expand this diagrammatically as follows. It's the identity minus the diagram that looks like so. And how do you see that? Well, it's just a very easy fact. This map is V tensor W, of course, goes to W tensor V. And on the right-hand side, here, it's V tensor W goes to, well, this guy gives you V tensor W back. And this guy gives you, they wedge together and then include. So when they wedge together, it becomes V tensor W and then it includes. So you get V tensor W minus W tensor V. So these flips of the tensor factors become some linear combination of these other diagrams. For example, and say more generally, if we want to cross a K and a L guy, so that's like wedge K CM tensor wedge LCM, we're going to switch those two tensor factors. We can write that as a linear combination of diagrams. It's like an easy exercise like this one here. Something like this, I might get it wrong, but just J 0 up to K. This is assuming K is less than L. There's some bounds here. And so you have a diagram where you send back this J guy across, and here they send across L minus K plus J. So this guy starts as K, this guy starts as L. Then after you do this, this guy goes up to L plus J, and then it becomes L. Here, this one declines to K minus J. And then it gains back K and it gains back J and gets to K. Okay. Oh, and then I think it's like minus 1 to J. So like, from like a heuristic perspective, you have these two guys and they want to pass each other and they somehow do so by like exchanging some particles across, linear combination of those. Okay, so well, it's not super interesting, but this becomes much more interesting when we switch from G. So G was our semi-simple Lie algebra. We can switch to the quantum group UQG. So this is a quantum group, which I just regard as an algebra over, say, rational functions in Q. Again, you could work over some smaller ring inside of here. That's analogous to this kind of prime characteristic stuff we were talking about. And this advantage of switching to this quantum group is that these crossings become much more interesting. So it's no longer true. So there's an interesting isomorphism from V tensor W to W tensor V. So interesting isomorphism, not just the flip of tensor factors. This is the R matrix of the quantum group. What's nice is that the stuff I did at the beginning works fine for this quantum group. So these diagrammatic descriptions, basically, every time you see a number, you replace it with a quantum integer. So for example, if you have this UQSL2, it has a two-dimensional representation, which I'll call, which is like just this field. This field breaks them twice. So just like the, and instead of C2, you have this C. And then, so this circle here, that's a circle labeled 1. So before it was, you have C goes to C tensor C goes back to C, and now it's CQ, the field, it goes to CQ squared, tensor CQ squared goes back to CQ. And this circle now, instead of just getting you the scalar 2, gets you the scalar Q plus Qners, which is known as quantum 2. Okay, so there's this like small science, not very complicated, where you change from using integers or using binomial coefficients using these quantum integers, quantum binomial coefficients. And with that change, all this diagrammatic description works for the quantum groups as well. And so, and also, not just that, but also these descriptions of the braiding, this isomorphism, also work using the quantum group as well. And they allow you to change this braiding, this interesting thing, to such a linear combination of diagrams. And that's good because of following this theorem of Rishetik and Turayev, which says that the quantum group, more formal version of saying this, let me say it informally, the quantum group can be used not invariance. Let me explain how this works. So you have a quantum group. I mean, you have a knot. Let me just take this trivial knot, but drawn as a figure 8. So you have a knot, and then you have a projection of the knot or a link. I'll say the word knot, but really I mean link. Like it could have more than one component. We'll assume that our knot is each component of the knot or link is colored with a representation of our quantum group. So we have some fixed quantum group, UQG, and then we have some representation V along this knot. And then we're going to use this to define a knot invariant. The way we do it is we analyze this knot, projection of the knot from top to bottom. We start here with the trivial representation because we see no tensor factors. And here we see a cup. So we go to V tensor V dual. And then here we see a crossing. So we go to V dual tensor V. We apply this braiding map. And then we have a cup, cap here, whatever it's called. Cup, I guess. So we go back to the trivial representation. And so we have a linear map from this field to the field, and that map is multiplication by some scalar, and that scalar is the non-invariant. And it happens to always be a Laurent polynomial, not just the arbitrary rational. Oh, well, details. So now that we have this, diagrammatics, what we can do is we can start with the knot projection, maybe oriented. Then using our rule like so for the crossing, then we turn this into a linear combination. So this kind of rule may be sometimes called a skein relation. Using this skein relation, turn this into a linear combination of closed webs, and we can divide each one, and then we get our non-invariant. This was especially like easy to do in the case of SL2. So if G is equal to SL2, then that relation there is a famous Kaufman bracket relation. So this just becomes the identity. So these are C2 tensor C2s, and you get the identity minus the cup cap picture, like a special case of this one here. But this 2 is now the trivial representation, so I don't see it. Instead, I see a cup cap. The crossing becomes this identity minus the cup cap. Sorry? Yeah, it's true. So this relation here these relations are, again, at q equals 1 in the regular algebra. And if you do it with an arbitrary, if you do it with q, you have some power of q, like maybe q squared here and q to the j or 2j or something here. Ignoring that, so maybe there's supposed to be a q squared here. You take your knot projection, you apply this gain relation, you turn it into a linear combination of these SL2 webs, which in this case just means, so like if you did it with this diagram here, you would get, well, either you resolve this crossing like so or like so. So you end up with this minus like something like q squared times this thing. And then you evaluate each of these loops. They're each loops, so they're all q plus q inverses. So this will end up being something like q plus q inverse minus q squared times q plus q inverse squared. Now, don't complain that it didn't work out right or something. This is not really supposed to be a serious calculation. Just a sample of what you might do. Okay, so and this is so this idea is called this Kaufman bracket. I mean, this knot invariant you get here is called the Jones polynomial. I mean, when J is equal to SL2, the knot invariant is the Jones polynomial. I should have said that. So this Jones polynomial existed beforehand. I think even this Kaufman bracket method was maybe known from one. I mean, I don't know. It's all happened about the same time before my time. So there's this Jones polynomial, and it can be evaluated using the Kaufman bracket. And you can see it as a special case of this Reshetikhin-Triaev theorem, where you start with your knot invariant. You want to apply this braiding. You take the braiding and you turn into this diagrammatics like so, and you get a linear combination of these closed webs, and then you apply this. Now, I don't think it's actually a particularly efficient method of computing the Jones polynomial, or a particularly efficient method of computing these knot polynomials associated to like SLN. So now if you want the knot polynomial associated to SLM, which is called the specialization of the Humphrey polynomial, you can do it using our diagrammatics. You start with your every crossing you see, you write it like so, and then you get this linear combination of closed webs, and you evaluate those closed webs, and you get a knot polynomial. So in fact, I guess I should say this, when G is equal to SLM, and you only use the standard representation, not a component of that link with CM, then this is also like known from a long time ago, and it's called goes to a paper of Murakami. So this was Greg Kupferberg's motivation for advocating the introduction of these web categories, or what you called spiders, so that you could evaluate these quantum group knot polynomials by this method. But I won't talk too much more about this. Any questions about that? It's a good question. So he asked, what do you do if you get a web? Like, imagine I was doing this. Let's just do it now. Let's just do the exact same thing, say in SL3. So if you follow my description there, I'll get something like, I don't know, some power of q times this will be the crossing. So this thing, instead of looking like that, will look like so. And then, and this one is labeled 2, 1, 1. And then you'll need to use some of those other relations, which are long erased, to tell you how to evaluate. So you have to use some of the other relations to evaluate this thing. And maybe it's not super obvious that there's a algorithm that uses those relations that allows you to evaluate every such closed web, but it's possible to prove. There somehow must be a unique evaluation of each closed web, because we already know that this, like, but accepting our theorem, we know that such a closed web corresponds in our category to a map from the trivial object to the trivial object. And this, of course, the only maps of the trivial object to multiplication by the scalar. And so if you accept the theorem that our web category is equivalent to the representation category, in that web category, this thing must be equal to some scalar. So there has to be some way of deducing this from the relation. Any other question about this part? Okay, so should I go till 12? What's the exact schedule? Okay, so now I'd like to explain how we proved our theorem, which uses this Howe duality. I guess it won't be time to complete today, but I'll start now. So it's actually, I mean, a pretty simple idea. So if you take the representation Cn tensor Cm, Cm tensor Cn, this is an action of the Lie algebra I started with, SLM, and also has an action of Lie algebra SLN, but just for, so no one ever gets confused between which is which, I'm going to call this one GLN. I mean, GLN and SLN are not quite the same in the algebra, but it has action of GLN. So I'll talk about SLM and GLN. Okay, so it has a left action of SLM and a right action of GLM. But if you think about this as M by N matrix. And then we can take the exterior, and these algebras that generate each other's commutative. So another way of saying that is that the map, actually, well, first let me switch to some exterior power. So I can take some exterior power of this CM tensor CN, the same is true. And now here's the lemma of this Howe duality is that the map from U GLN to the endomorphisms of this wedge K CN tensor CN as an SL M representation, that this map is surjective. So this is very analogous to what we saw toward the beginning of the talk when I said that the map from the group algebra of SM to CM tensor N is surjective. It's sort of like a special case in some sense. It's slightly less, so this is not too hard, but we can even describe what the kernel is. So that's our kind of goal. So I'll probably come to that next time. But so okay, so next time we'll describe the kernel. But how is this related to all this stuff I was talking about with webs? Well, this exterior power of CM tensor CN, I can think of it as exterior power of just a bunch of copies, direct sum of n copies of CM. And then I can see, oh, I have an exterior power of a direct sum that's the same as direct sum over all exterior powers of each piece. So this is the direct sum over all sequences, K, 1 up to Km, or K1 plus Kn plus K, and wedge K1 Cn. The biggest problem in this topic is giving our n's and m's confused. Okay, now. So these, and so this space here is the same thing as the direct sum over pairs of such sequences K and L of some SL M between such tensor products. So exactly what I wanted to study. So my category consists of such tensor products and HOMs between them. And those tensor products and HOMs between them can all be realized by this theorem from this other Lie algebra, SLGLN. So my category, I was interested in such HOMs like so, and they all come from UGLN. And in fact, what do they look like when, how do they look when they come as diagrams from GLN? They know the universal enveloping algebra GLN has these natural generators, Chevrolet generators, FIs and HIs maybe. So EI corresponds to a matrix which is like so, a 1 in the I row and I plus first column. And then it, under this action here, this EI gets mapped to the following thing, put it over here. So it gets mapped to a diagram, I and I plus first strand, I and I plus first strand, and sends a 1 across this way. Label here Ki, another label here Ki plus 1. The label Ki has been increased and the label Ki plus 1 has been decreased. So EI corresponds to this diagram. And to see why that is, or why something like that should be true, when we did this decomposition here, so I kind of ignored CN, right? I just set it out like so. But these copies of CN, these different copies of CN, they correspond to the basis vectors in CN. So this EI is like taking something from the I plus 1 basis vector and sending it to the ith basis vector. Or another way of saying the same thing is that this thing here is actually a weight space for the action of GLN. So it's the K1, Kn weight space. EI takes you from that weight space, so here we're in this weight space, K1, Kn as a Giant representation, and you end up in this weight space, which is the same as taking that K1, Kn and adding alpha I, where alpha I is the simple root with a 1 and -1 like so. And that's what EI does. You know, it takes you from some weight space and adds the alpha I to the weight. And it turns out it's exactly realized by this diagram. So in this way, we see this surjectivity onto our endomorphisms that we're interested in, these HOMs, and we see exactly that these EIs correspond to some maps that we're interested in, like these maps where one comes across. And so the only thing that remains, as I said, is to describe the kernel. So that's what I'll talk about next time.
Questions, comments? Actually, there was a comment from Martina Balagovic during your talk telling us the history of the P and the Q.
Oh.
It's supposed to be a joke that Victor Katz did in 77.
Oh, wow.
And he was looking for words and came up with queer and periplectic. Okay, so if there's no more question, I guess that it's lunch.